Apologies for last Tuesday. I had a bit of a back problem, which is, I think, getting fixed up, but mostly because I'm on drugs, anti-inflammatories. So I've got to be a little careful when I'm moving around. Now, it puts us a little bit behind, so I changed the schedule on the web page. If you go to the web page, I've kind of restructured Lecture 8, and we're really doing material in Chapter 7 and Chapter 8. We're going to finish off some ideas about probabilities, uncertainty, just sort of concepts today, and about there's a concept called Bayes' theorem, which has to do with learning from about, I guess, changing your beliefs. Okay, learning from information. But we want to think of it as you're in a game and you see things happen, how would you change your beliefs when you're not sure exactly what's going to happen? Okay, so that's kind of the idea. We're going to use the notion of inverse probability. We're not even going to put a theorem down or ask you to memorize it or use it. But it's just a way of thinking about how to learn in sequential games. Okay, so we're going to spend a little bit of time doing that today. But just before we do that, I'm going to talk a little bit more about these three different ideas of probability. Okay. Just be careful when you're reading in Chapter 7 and 8, because some of it, the only problem with this text is the material and the mixed strategies. Okay? They get a little bit carried away with the technicalities of it. It's really only suitable, I think, for Stage 2, Stage 3 econ students who are kind of getting into the mathematics of game theory rather than the conceptual sort of stuff. What I'm going to try and do is talk around this idea of mixed strategies. We'll draw a little diagram, okay? And the diagram will help us understand why mixed strategies are important, how you can think about the idea of surprise in a game, come up with a little better, deeper understanding of Nash equilibria. And then it turns out in the latter lectures of the course, one lecture when we talk about what's called evolutionary game theory, we'll come back to the same kind of diagram, okay? But as you're reading through the text, you'll see these equations, you'll see the graph, and you probably think, oh, how does he get from here to there, okay? Well, I will not ask you that kind of stuff on an exam. It's not an algebra course or, can you take the math and put it into the diagram. But you can kind of look at a diagram and sort of read it and interpret it. That's the main idea, okay? Just wanted to exercise that caution in Chapter 8 because it can get a little bit technical. And for next week, we should be getting into Chapter 9 on signaling and screening kind of games, and then we'll look at Chapter 10 on credible commitments. Okay. Now, you've all done these things. We've got a bunch here. Got some there. Anywhere else? People handing? Did some come down to the front here? Anybody else got any more? Okay, well, this was a question on diagnostic sort of things, and it actually turns out to be almost identical to a question which is given to doctors to try to figure out how they would interpret diagnostic tests. And it's a little bit frightening, the replies, but we'll eventually get into them. But it works with the idea of probability, and the language of probability is important for our game theory because essentially we want to be able to think about how rational people think about uncertainty. Okay, now we're all not as rational as we might like to be, and sometimes thinking about uncertainty is quite difficult. Okay, especially as you try to put several uncertainties together and do some reasoning, much less for yourself, much less for other people. Okay, and so I started with this little chart on the board here that, or on the overheads, which kind of looks at probability as a qualitative thing. Okay, I mean, most of us, I think, in our life, we get pretty skillful at. We don't know what's going to happen, but we can sort of say, well, this is more likely than that. Okay, if you ask us how much more likely, it's quite difficult to do, but you get this idea of a qualitative ranking of likelihood of things, and really, a lot of things depend upon the information we have, okay? Or if we don't have any information on things, you haven't got a clue what's going on. But as you pick up your kind of skills in life, you get a handle on what your own abilities are, what the kind of random things are you're going to meet in the world, what other people's abilities are, and you can grade these things by this language of qualitative probability. So, like almost certainly, highly likely, the stuff at the top. Often we use this idea of it's a better than 50-50 chance, okay? It's like there's a coin toss, which tells us we're really not sure what's going to happen. The coin's going to come up head or tails, but we think something's more likely than that, okay? Then it's going to come up ahead. So that's a better than 50-50 chance. So that's a useful benchmark. If we're perfectly certain, yeah, we'd put on 100% probability. If we're perfectly uncertain, we put on 0. But we're never perfectly certain or uncertain about anything. But so we use this language, okay? Now, in the course, we need to be a little more precise. And in the history of game theory, it really developed out of, remember that definition that Meyerson gave? It was the science of rational intelligent players, or mathematical models of. So mathematics and statistics played a large part in the early development of game theory, and they used the language of probability to kind of represent and understand uncertainty. So that's what we got to in the end of the last class. We came up with trying to interpret probabilities, and I said there's really 3 ways you can interpret probabilities, okay? And they're connected, but they're quite distinct. The formalist guys, what they like to do is they like to have a language, a mathematical language, like they'll give you a normal probability distribution, you know, that little bell curve thing, or they might say, oh, there's a Poisson distribution, or here's a gamma distribution, and all of these probability distributions satisfy some really beautiful mathematical laws, okay? So the formalists tend to look at the whole problem as one of mathematics, you know. They're not so much worried about applying the ideas, though a lot of them are, but it's the formal mathematical theory of probability. It has to satisfy certain axioms. Now, if you look in Chapter 7, you'll see at the end of the chapter kind of a nice discussion of probability. I mean, I don't tend to agree with all of it, but it's not a bad little textbook discussion. And it talks about probability as satisfying certain axioms, like probabilities have to be greater than 0. They have to be less than 1. The probability of A plus the probability of B, if you've got 2 events, you want to look at the chances of either of the events or both of them together. That's got to satisfy some rules or laws. Okay, so that's the formalist idea. Is you have these axioms, you figure out these mathematical formulas which satisfy those, and that's okay. You know, so that's as far as the formalist goes. The frequentist guys sort of think, well, no, probability isn't just math. It is. But it has to do with proportions, you know, proportions of symmetric things. Like the coin toss is the classic example. You know, you toss your coin, as I'm sure all of you have done. You know, you just one of those things at a boring Saturday night. You just flip in your coin just to see how many heads you can get, and you're practicing your random walk kind of things. Okay, and so you're just flipping your coin, and that's the idea of repeated things which are almost the same, but not quite the same, because if they were exactly the same events, you get exactly the same result each time. But there's something that changes just a little bit, and you don't really know what's going to happen, okay? Or you might have a deck of cards, okay? The deck of cards got 52 cards. There's, you know, clubs, hearts, diamonds, spades. Each of them has different numbers on them. You shuffle them up, and you're not really sure what you're going to draw. Or if you're playing poker or other kinds of card games, there's little bundles of things. You got to try and figure out what are the probabilities of these things, okay? So the probabilities there are sort of thought of as, well, if you played these games over and over and over and over again, shuffled that deck, rolled those dice, drew balls out of urns, you know, flip coins, all of those are nice repetitive events, and probabilities should really mean the frequency, the long-run frequency that you would have if you played those events over and over again, okay? And that's not an unreasonable idea of probability. It's just that it doesn't apply so much to a lot of business situations or strategic situations. Because in strategic situations, almost all of them we've looked at, they're just one-off situations, right? Now, we'll look at repeated situations and what you can learn in repeated situations from different kinds of outcomes. But we'll see we're not just going to look at the relative proportions of successes and failures in these repeated situations. We want to, you know, if we're in a repeated interaction situation, we're going to look in the past and we're going to see if this guy was helping us out or not, or whether we should punish him in the future. And what'll happen if we decide to defect or cheat in an agreement, and what's going to happen in the future isn't necessarily what's going to happen in the past, because it depends on what strategies people have. Okay, so we want to think about it more than just look at the counts and proportions. So the frequentist idea is useful. I mean, you get measurements, you take frequencies, you come up with an idea of proportions. But I want to spend a little bit of time on this subjectivist idea, so that we think of probabilities as representing the degree to which you're uncertain. Now, you remember in this qualitative probability thing that I had up here, this chart, which comes from a there's some mathematical psychologists who were trying to map common language that people use or descriptions to numerical numbers. Okay, they're saying, well, when people talk about things being in a really good chance of or highly likely, they're thinking in the area of 80 to 90% of. Okay, when it's just probably or better than even, it's around 50 to 60%. It could be a little bit of a range, but not a lot. So the psychologists would try to use ordinary language and people's describing what their beliefs are in words to assess numerical numbers which represent these probabilities. Okay, and so then the experimental guys come in and they sort of say, it's a little dicey here. Okay, and why it's dicey is that I could say here's an event. Like, for example, one of the most surprising things in my life was that I got divorced. When I got married, I loved my wife. She loved me. We had kids together. Came to a new country, new job, everything. And 10 years later, I'm separated and divorced. It didn't occur to me. You put if I was to say, there's no chance of that happening, which is what I believed it. Okay, but then you kind of look at the statistics and things like that, and you think, wow, 60% of people who get married. I'm not one of those. But on the other hand, I turned out to be one of those, and it was really, really surprising. I'm glad it's a long time ago because it was very painful. Those kind of relationship breakups are very difficult for people. Now, the idea is, if I was describing in language, it's really what someone, I think it's George Bernard Shaw said that your second marriage is the triumph of hope over experience. You've had one example where it didn't work and you still keep going. I've got a couple of friends. My good friend Glenn Harrison, he's been married 3 times. Mark Blaug, this Nobel Prize winner. Oh, no, he's not Nobel. He's almost Nobel Prize winner. Erskine visitor who is here, 80 years old. He's been married 3 times. You think, you're going to learn? 0 out of 3, 0 out of 4. It's like, on the other, it doesn't stop you from having relationships, but the language we use, we're not, it's kind of, isn't just what we believe, it's almost what we hope, And on the other hand, I want to introduce you to a way of not just saying what people say as chances, but where they'll kind of put their money if they had to bet on something. And so what I'm going to do is show up an example from the sports betting bookies where they come up with prices or odds which reflect their beliefs about various kinds of sporting events. And I think I told you earlier in the course that one of the, I think, best experiences I've had was the day that I spent up with the sports betting bookies at the TAB. And it was, just a fascinating experience working with these, I was going to say these guys. Well, they are guys, but there was one girl, operations researcher, and 5 other guys. And they have to set prices for they get paid to do it, and the TAB makes a lot of money from their setting these prices. And basically, these prices reflect what their beliefs are about these events. Okay, so let's have a look and see. And this idea here is to take this notion of what we're going to do for the next 5-10 minutes is just have a look at this idea of subjective probability. So you realize that these probabilities are subjective. They are your beliefs, okay, or my beliefs. We say the adjective subjective often means, it's terrible. Don't you want some sort of objective thing like tossing coins or drawing balls out of urns or, taking things out of decks of cards? Well, yes, you do, if you can see the deck of cards, if you know what kind of urn it is, you know what kind of coin it is. But in business relationships and human relationships and strategic interaction, there's lots of things that happen where you don't have that kind of experience from the past. And even if you did, you still have to interpret it and make sense of it, okay? And so it is subjective. Different people will have different information. They'll come up with different sets of beliefs. Now, there's sort of an idea in this subjectivist theory that if there was a long run and these things were repeated, then everybody would kind of converge to the same belief. But the fact of the matter is, we never get to the long run. We all die before then, and we all have different experiences. So our beliefs are personal and subjective, but we can measure them as well. And that's we use this adjective called operational. So we think of operational subjective beliefs. Now, this is my little attempt to convince you this is kind of an interesting area. I pulled these odds off the web page this morning for the World Cup for rugby. Okay, and so if you go to the TAB site, then there's all kinds of bets that they offer, and here they're betting on. They're offering odds on New Zealand being the winner of the Tri-Nations, South Africa being winner of the Tri-Nations, or Australia being winner of the Tri-Nations, okay? And down here, they're offering odds on the All Blacks winning the World Cup and somebody else winning the World Cup. And if you keep going through, they've got, I think they have Japan at like $5,000, they're paying $5,000 on Japan to win the World Cup. Okay? That means if you pay them $1, they will pay you $5,000 if Japan wins. Okay? I mean, that's $5,000 is a lot of money, right? You're going to take that bet, Megan? Because most of us know we're throwing away $1 really, because we don't really think Japan's going to win. Okay, and this but the TAB they don't want to put down like they put down $5,000. What if they put like $100,000? That'd be a beautiful payoff to win, wouldn't it? For $1, I might even take a risk on $100,000. I mean, it's almost like throwing it away, but it's not as bad as throwing it away if they're only paying $5,000. Okay, so the idea is that they're setting these odds. There are other people who are going to take some actions which are going to leave the sports betting bookies at the TAB at risk. And one interesting thing about the way they set these odds is that it's not that they're really trying to balance the books in the market, but they're putting these prices out there and they're saying, look, this reflects our beliefs. If you think you can outpredict us, then go ahead, bet with us. Okay? And that's the idea of operational subjective beliefs, is that it's not just, I think this thing's more likely than that. I'm willing to put out some prices and say, well, okay, you bet. You guys bet at these prices. So let's have a look at this set of prices here and just see what they mean, okay? So you're going to the sports betting bookies at the TAB. They have these things they call bets, option number 492, $1.40 on the All Blacks if the All Blacks win, and $2.80 on any other nation if any other nation wins. So I've got another handout for you so you don't have to do so many calculations. Thank you. Just up behind you will be fine. Okay, now, when I was playing we did the card game, and we're thinking of these contingent payoffs, it was whether Megan was getting a club or a spade. Well, here the contingency is the result of an outcome of a game. Okay, whether the All Blacks win the World Cup or whether some other team wins the World Cup. Now, what I've done here is we want to think of this. If I make a bet on the All Blacks, so that's New Zealand here in blue, or some other nation in red. Okay, then what they're saying is, look, if you pay me $1, then if the All Blacks win, I will pay you back $1.40. But I'll pay you nothing if the All Blacks lose. Okay, if I bet on some other nation winning, then they will pay me. It could be England, it could be France, it's just any other nation. Then they will pay me $2.80 or nothing. So this $2.80 or nothing, or $1.40 or nothing, is a contingent payoff. It's an uncertainty. We don't know what that outcome is going to be. Now, the way in which the odds are expressed sometimes can be a little bit confusing, okay? Because it's not confusing. It's better to think of it in a different way. Is that I'm paying the TAB $1, and then they're going to pay me back $1.40 or nothing, okay? But suppose that I only paid them half $1. Only a fraction of $1, okay? So let's take a half. So they would pay me back 70 cents or nothing, okay? Now what I've done here is I've tried to figure out what's the fraction I have to pay them, so I would either get $1 or nothing. And if I take the reciprocal of $1.40, that comes out to be about 36 cents. So it's kind of like, think of it this way. I pay the TAB 36 cents, and they will give me a proportion of the $1.40 or nothing, which turns out to be $1 or zero. Now that concept is kind of useful because I want to think of it as a ticket, a unit ticket on the All Blacks winning. Okay, so the contingency is the All Blacks win or they don't win. If they win, I get $1, and if they don't win, I get nothing. Okay, and the price of that is 36 cents. Now, really, this is really no different than you go into the store and you're saying, look, if I spend $1, I'm going to get 2 kilograms of tomatoes. And then you sort of say, this is your standard question in grade 7 algebra or something like that. Well, how many dollars do you have to pay for 1 kilogram of tomatoes? You just take the reciprocal. Okay, it's like I pay 50 cents to get 1 kilogram, or for $1 I will buy 2 kilograms. So it's just a different way of expressing these prices, but it's a useful way of thinking about it, because what you can think of is, well, what if you bought a ticket on New Zealand winning, and you bought a ticket on some other nation winning, right? So you're going to get $1 back from the TAB anyhow. Okay, if some other nation wins, you're going to get $1. If New Zealand wins, you're going to get $1. How much do you pay for that? Well, what you pay is 36 cents and 71 cents, and that adds up to $1.07, doesn't it? If you go through all of the 2 outcome bets in the TAB and Center Bet or wherever else in the British bookies, those 2 outcome bets almost always add up to about $1.06 to $1.08 for those guys. And the way they think of it, that's their take on a balanced bet. So, if this side of the class bets on New Zealand and this side of the class bets on the rest of the world, and if there was an equal number of these tickets bought, then the TAB wouldn't be at risk at all, okay? Because what's happening is, they're getting, what are they getting? $1.07, okay? And they're going to have to pay out $1 for sure, either to this side or to that side, but they get 7 cents. Okay, so that's called a guaranteed bet, or if you like, it's the bookie's take from a balanced outcome. But it turns out they end up not balancing their books, so they do accept risk. But if they did have a balanced book, then the sum of these 2 reciprocals would tell us what their balanced book would be. Okay, so these guys, they want to make money. They're willing to take risks. They set these prices for these tickets that they offer on these various contingencies, but the prices they set add up to $1.07. Now you can only buy stuff from the TAB, right? Supposing the TAB, you sell things to the TAB like this. Okay, so I'm John Fountain. I go to the TAB and say, look, you're willing to buy at a red at, you're letting me buy at 36 cents and me buy at 71 cents. Why don't you buy from me? Okay, so well, first place the TAB is going to say, who are you? And rightly so, because how do I know I'm going to pay out of my debts? But supposing he did, okay, so then you'd think, well, okay, I'm going to sell the TAB a ticket on the All Blacks at 36 cents. I'm going to sell the TAB a ticket on some other country or any other country at 71 cents. So what's going to happen? I'm going to get $1.07, right? Now, one of those outcomes is going to occur, assuming, there isn't some sort of terrorist attack to the world, who knows, the referees cheat or something like that, whatever it is they might call it the game. But the idea would be, I'm going to have to pay out $1, but I get the 7 cents for sure. Now, what happens is, when you have to buy and sell, if you quote odds or prices that add up to more than 1, then you can be made into a sure loser. Okay, so and what I'm trying to describe is the TAB is not a sure loser, but that's partly because they only sell tickets to us. If we were able to sell tickets back to them at the prices which they quote, sorry, it's getting in the way. Go around. If we were able to sell tickets back to them, so they had to buy or sell at these prices, then if they quoted prices of 36 cents and 71 cents, they could be made into a sure loser. Okay, got that idea? So it's just sort of an intuitive idea, but it happens to be the first law of probability. Here's the probability of event A, and the probability of event not A have to add up to 1. Okay, the total probability has to add up to 1. Well, the idea is that if those probabilities are prices, and those prices if those prices reflect your willingness to transact, to buy or sell small amounts of money, then to avoid being a sure loser, you have to make those things add up to 1. Okay? So if you think of these prices as probabilities, and we get rid of the track take, and we just sort of keep the relative size of these, then what we can think of is the TAB's probabilities on the All Blacks winning are 1 out of 3, and for somebody else winning, 2 out of 3. Okay? So if you get rid of their track take, and you're sort of thinking, okay, what's their guess when they set these prices at these teams winning, at the All Blacks winning or not, it's 1/3. Sorry, 2/3 for All Blacks, 1/3 for some other country. So these prices reflect their beliefs, and that's when we're talking about in game theory. When we're going to start, we had these probabilities. So, for example, in the game tree, the card game tree, we had a 50-50 chance. And why would I assess 50-50 chances? Well, as long as the deck is shuffled up and it's well shuffled, I know there's half clubs and half spades, and everybody else knows there's half clubs and half spades. And we all kind of agreed that 50 cents would be, if we had to put out bets on these, which we don't want to do, but if we did have to, like the TAB does, then 50 cents would be the price that we would put. Okay, so that's the way we will interpret the probabilities. Sometimes they won't just be 0.5. Sometimes it'll be something different than a card game. And we'll describe these probabilities as people's beliefs about things. Okay, Jason's going to sell me his car, and it's and I'm sitting there thinking, is it a good car? Or is it a bad car? He knows, but I'm thinking, oh, it's like a coin toss for me because I don't know. But most cars out there are pretty good. So I'm going to put on a probability like that. Those would be my beliefs, and that probability will be my willingness to bet a small amount of money on the car being good or bad. Okay, so that's the idea of subjective probability. Okay, what else have I got here? You do the same thing when we take the reciprocals for the other guy, and I just put a little summary down here of the important things about probability that you want to keep in mind. We don't usually have one probability. We have several probabilities, okay, for various things that could happen. So we call those probability distributions. The probabilities are going to be numbers, typically fractions of some sort. If you think of them as your beliefs, then they are subjective, but they can be operational in the sense you can measure subjective things not by what people say, but by what they do, what they're willing to bet on or not. And I put a little caption here. It's like, if you say a probability of something is 0.8 or 0.9, 90% chance of you passing the course, then if you're willing to back that up with a ticket on you passing the course, that you're willing to buy or sell to somebody else for 90 cents. Okay, that's the idea. You would act like a sports betting bookie and say, okay, I'll put out some odds on this, on my passing the course or not. Let the bets roll in, but only a small amount. And we say only a small amount so that you're thinking, oh, I'm looking at all the bets here. Maybe I should cheat a little bit and not pass the course, or pass the course. Kind of fix the game. Or we don't want your wealth to be totally absorbed in this. You're thinking, I don't want to do this because I can't afford it. Okay, so it's just a small bets, but you're willing to back up what you say by a little bit of money. Now, this is an unusual concept. If you take any statistics courses or any economics courses or management science things, in physics, people have these models, these probability models, okay? Economists, physicists, management science people, operations researchers, they're all great at these things. They never have to back up their predictions with these models with money. There's been some people that saying professional journal articles should be run that way, so that if you're going to put out a hypothesis or a model, and you're going to forecast something, you should be willing to back it up with a little bit of money. Okay. Let's, sorry, let me just go back to this last little thing here. They're operational. The coherency idea is what I said about the probabilities adding up to 1. There are all the other laws of probability you can derive from this behavioral stuff about buying and selling tickets on contingent events, and in such a way that you have to satisfy the laws of probability. That's what the coherency means. But it also means if you don't, you'll be made into a sure loser. Okay? And then the last thing is that anything that you're going to offer odds on, you really want to know something about the situation, right? And the odds that you will offer will depend on the situation. The sports betting bookies, they do a lot of research work, okay? They're studying, home and away things. They're studying weather conditions. They're studying referees. They're studying they're keeping track of whether the star players are available or not available, the past track records of these things. They've got a whole bunch of information that they put together in their heads because they don't seem to have spreadsheets that do their models, and they come up with a number. And that's what I want you to think about with your subjective probabilities. In the game trees, as we're trying to work these out, various things will happen, and you'll be looking back at the game and trying to figure out what it is that's going to happen in the game. Now, to get you an idea of how you might use that probability reasoning, I've got this little example which, let me build up for you. It's the one you just tried. I'll put the text up. It's a kind of example where we don't have any payoffs. We won't have any payoffs at the beginning because we just want to think about working our way through the game tree and figuring out what you might believe, how you could use probability theory to help you out, figure out what you should believe at various points in the game. So in this little example, you're a doctor. There's a radiologist. Radiologist gives you a test result out of a mammogram, and the test result could be positive or the test result could be negative for breast cancer for your patient. Okay, so for the moment, we'll put the patient aside. She's not a player in the game. We've got the doctor, that's you. We've got the radiologist, and then we have this uncertainty about whether the person has breast cancer or not. Okay, so I've put these down on the handout for you, and I've put 3 players. We've got nature, the red player, and the idea is nature is this fictitious player who, when there's some uncertainty, we're representing the uncertainty as a choice. Okay, not like a conscious thing necessarily, but there's some sort of choice. Choice could go either way. Yes, you have breast cancer. No, you don't. Okay, it's just binary. It's not like the seriousness of the disease. The radiologist can come up with a positive, say it's a positive test result or a negative test result. Okay, just 2 outcomes sort of situation. Now we're going to put those 2 together, those 2 ideas, in what we call a truth table. Now think of this on the left-hand side as a proposition. The patient has the disease. It's true they have the disease. Yes. Okay, could be no, but the proposition is they have the disease. The test result comes out positive. Okay, that's a proposition. The test is positive. It could be true, it could be false. Okay, if the test is negative, it's going to be false. So what we do is we put together the 4 logical possibilities. And 1 is going to be true, 0 is going to be false. So we have, yes, you have the disease, yes, the result is positive. Yes, you have the disease, the result isn't positive, which means it's negative here, okay? You don't have the disease, but you do get a positive result. You do have the disease, or you don't have the disease, and the test indicates you don't have the disease. It's a negative result. Okay, so there are 4 logical possibilities here. This one in this column is a true positive. Okay. This one in this column is a true negative. In this column over here, we have what we call a false positive test, because the test is positive, but you really don't have the disease. Here we have a false negative test, and it's a negative test result, but it's false because really you do have the disease. Okay? Now, let's draw a little game tree. We're trying to represent this information in a strategic situation, forgetting about the payoffs for a second, but just think about the order of moves here. Nature moves first, gives the person some genetic material or environmental things, whatever it is. Yes, they do have cancer. No, they don't have cancer. Okay. The radiologist sits here at the blue node, and they have their test apparatus, okay? So they're taking a mammogram, complicated kind of test with a complicated technology and software to decode things and to read and interpret stuff, and he comes up with a result. But we put this information set around these 2 nodes because the radiologist doesn't actually know whether you have cancer or not. Okay? So they don't know whether, I mean, they could be here or they could be there, but they have to make a statement. It's like, I've got these results from the test. The test indicates plus. Yes, you do have cancer. The test is minus. No, you don't. And there could be shades in between, but we'll just keep it binary, okay? So I've put the possible decisions or reports of the radiologist going in this direction. Now I put this little loop over here because I want to make sure that you don't think these lines are kind of intersecting and crossing in some way. And you'll see in a moment why I've kind of grouped the outcomes this way, because when I look at you as the doctor, your information sets are going to be like this. Okay? And this pattern, this particular geometric pattern, will be useful for us when we're looking at these screening and signaling games, where your employer, the employee shows up. You've got some information about their test results and things like that that's objective in the sense everybody sees what that is, but you don't know whether they're going to work hard or not. You don't know whether they're honest or not. Okay, they could be doing a little shirking on the side, or they could be working really hard but not on what you want them to. The type of person that you just don't know. Okay, or you're a bank, you're going to loan money. Is this person going to default on their loan or not? Okay, you're a health insurance company. Somebody comes to you for health insurance. Does this person really have they say they don't have any diseases, but do they? I don't know. Okay, so the idea here is the doctor is going to be making a choice, but all they're going to see is the positive result. They can't see behind that positive result to whether nature has chosen yes or no. So we put a loop around those two nodes. Similarly, these two nodes here, they're indistinguishable. That's what the information set does. It says it's just like one big node. I know that the test result is negative, but we have a yes or a no. Okay? Now, supposing we have some information. Okay? Now, what I've done is I've taken this material from Gigerins. There's little examples. And this information isn't related particularly to this patient, but it's background information. And what you can think of is like there's 1,000 results. And the results are where people have gone back and they've actually looked at the radiologist's results and said, okay, they've said they've had positive tests, they've said they had negative tests, they've taken those people and checked out, do those people actually have cancer or not have cancer, okay? So it's like really comprehensive, full-blooded information. There's 1,000 pieces of information, and it breaks down like this, okay? There are 7 of these true positives, and there's 1 false negative. So 8 actually have the disease in these 2 columns, but only 7 out of 8 show up as having a disease. And that means that the test, it's not a bad test, okay? It catches 7 out of 8, but it misses 1 every 8. Okay? So that's called the specificity of the sensitivity of the test. If there is something, is it going to pick it up? Well, it does most of the time, okay? Now, look at these other 2 columns. There's 922 plus 70 is, 992 cases here. 992 cases out of 1,000 where there's no disease. So this obviously isn't a big disease, right? Which is in the text description of this, it was like 8 out of 1,000 women will typically have the disease. So it's a serious disease, but most people don't have it, okay, in this little example. However, if you look at 70 out of that 992, are coming up with a positive test result. Okay, now let's just do some little calculations. What are the chances of the disease? Okay, the chances here we're thinking of is looking at these counts, and we've got these counts from really good information in the past, and we think, well, 8 out of the 1,000, these 2 columns have the disease. So we're going to put in an 8 out of 1,000 there, okay? There's 2 other concepts which we want to think about. This has to do with the if you like, the sensitivity and the specificity of what's called the test, the diagnostic thing, the radiologist's equipment, their software, their technicians, their ability to take this stuff and accurately describe whether or not, sort of pick up, give a positive test result when there is a disease, give a negative test result when there isn't a disease. Okay, so that's what we use this language here. We say the probability, and just think of it reading left to right, the probability that the test result is positive, and the slash line here means given. Okay, if there is a disease, of which there's 8, 7 out of 8 will show up with a positive test result. If there isn't a disease, then that's 992. Okay, then only 7 out of 992 are going to show up with a positive test result. Okay, that's about 7%. So 93% of the time you're picking up the fact that people don't have a disease. Again, it's not a bad test, but it's not perfect. Okay? Now, supposing we just cross those guys out, because we're not interested in those. We're interested in, I'm sitting here as a doctor, I don't see whether they have a disease. I don't see whether my patient has the disease. What I see is this guy has given me a test result that's positive. What should I think about the chances of the person having a disease given the test result is positive? Well, if you look at the table, who has all the positive test results? Well, there's 7 people out of the 8 who actually have the cancer, but there's 70 who don't have cancer who get these false positive results. Okay? So you've got 77 people who are getting positive results, but only 7 of those really have cancer. So if you look at the little table like that and you kind of think it through, so you think, oh, okay, I can see what's going on. There aren't very many people who have cancer. The tests are imperfect. Because out of 1,000 people who don't have cancer, there's so many of those people, even though the test is a very good one, it's picking up 70 out of 992, okay, and saying they have cancer when they don't. You get a lot of false positives. So in this case, even though you get a positive test result, should you think, gee, I got cancer? Well, no, because if you look at the table, you think, well, the chances are really 7 out of 77, 1 out of 11. Even though the test would pick up, if you did have cancer, it would pick it up 87% of the time. And if you didn't have cancer, it would tell you didn't have cancer 93% of the time. If you got a positive test result, that's a different concept, okay? If you've got a positive test result, then the probabilities you're going to assess here are 7 out of 77. So, I mean, I'm going to look through, see what you've got on these test sheets. Tomorrow, I'll introduce you to another little question like this and see if you can use this kind of reasoning to figure out, what are the probabilities I should assess when I get to this point on the game tree. Now, we're going to use this pattern a lot. This is going to be the one where Jason's selling his car, and the car could be good or bad, and the fact that he's got it for sale worries me, okay? Because I know people who have lousy cars, put them on the market to sell them, and if it was a good car, why would he be selling it? Okay, so and we'll use that kind of reasoning just with that little table to try to figure out, I'm out here, I can't see behind what nature's doing, but I can take something from what Jason's doing, so that inference, just like you can take an inference here from what the radiologist said. So we'll come back and look at that tomorrow, and then we'll work at mixed strategies.